So Jesper is here to tell you more about developing smart contracts. This is a part of our online developers programs before the hackathon that is happening on the 1st and 3rd of December in Paris. So looking forward to hear more. I have no idea how to say your family name, so I'm not gonna try.
Well,
So
you're welcome to butcher it. So that's fine.
Listening, if there will be questions, you please say and write them in the Q&A. I will be here also to help with anything. Good luck.
Yeah. Yes, and you're free to interrupt me, Elad, if there's any questions coming up that seem relevant during the presentation. Then I'll just take them.
Introduce myself, actually, I forgot. Elad Mintzer, hi everyone. I'm the community manager of the Partisia Hackathon. Also here to help with stuff. Enjoy.
Thank you. Well, my name is Jesper. I'm working in the smart contract team and heading that here at Partisia Blockchain. And I want to share with you today some information about how you can develop your own smart contracts, what it actually takes on the Partisia blockchain. You may already have seen the presentations by Kurt and by Peter about what the Partisia blockchain is and what it offers, and also by Peter on what the architecture is and the overall concepts of the blockchain. If you haven't already seen that, then I highly recommend that you find them and go see them on the hackathon page. But you will still be able to follow my presentation, and you can go back to their presentations after this. Let me try to show you an agenda. And if at any point you have any questions, feel free to ask them in the chat or in the Q&A section, and then Elad will bring them to my attention, and I will hopefully be able to answer them for you. So the agenda for developing smart contracts, well, I kind of have two sections. I have an important section first that is about the tools. That is all the things that you actually need to be able to develop your own smart contracts. And we already have quite an impressive tool set at your disposal. So you will be able to use these tools to both for developing the contracts, but also for understanding what is possible with the contracts, seeing great examples of other contracts that have been developed, testing them, using them from a front end, and there's a lot of documentation and help available as well. When I've gone through the tools, I will move on to actually talk about what does the coding look like. So I'll show you a little bit about how you can use smart contracts, and then I'll dive into code. How do you declare states and actions of a contract? How do you create contracts that actually talk to other contracts? And finally, we're ready to tackle zero-knowledge computations, which is making your contracts much richer with the ability to actually compute on secret data that is secret shared, and use the Turing complete language that we've created for performing zero-knowledge computations on the blockchain. I'll start by diving into the tools. So this is everything you need to start developing your own smart contracts. And well, the most important tool for developing is, of course, a compiler, at least when it comes to smart contracts, because you will be writing the smart contracts in the Rust programming language. And when you coded a smart contract, well, what you need is a Rust compiler to compile it. But you probably want our compiler front end, which will do a lot of the heavy lifting for you. So the only command line you need the prerequisites first. You need to get the default Rust compiler. You need to get a Java runtime, and you need to get the Git versioning system. And if you've installed those prerequisites, which you may already have on your computer, then you can install the Partisia contract compiler by a single command line, and that is the command here on the left. And if you put that command into your shell, then it will install the compiler for you. So it's as simple as that to get the compiler.
Jesper, it might be relevant to, there's one question that might be relevant because it's a background about Partisia and EVM compatibility. And so maybe you can say that as well when you start.
Yeah, so on the EVM compatibility, I think Peter already touched on that. I think it'll be better to get back to that near the end when you've seen how it all works, and then we can talk about EVM compatibility afterwards. Was there a second question as well?
Yeah, but in general, Partisia is EVM compatible, but in another way. That would be, I guess, the answer, right? Like that it's more complicated. It's not as straightforward.
No, yeah, I think that's what Partisia is doing is different from what Solidity is doing. So it's not straightforward EVM compatible, but it is still a blockchain. So there's a lot of things that will be the same. But if you watch Peter's talk, you'll get he did a deep dive into how the Partisia blockchain differs from other blockchains, including the differences with the EVM blockchains. So I think that is a great way to get the answer to the question.
Where can you find the other presentation? I will send something here.
Yeah, you can send it in the chat because it's on the Hackathon page.
Yeah. Thank you. At the end, please let us know where we can find the presentation and whether more materials you intend to make available for later. Yes.
Yes, I'll come back to materials as well. So that's thank you. Well, I'll move on. So when you've installed the compiler, you now have a new tool that you're available for you, the Cargo Partisia contract tool. What this tool actually does is that it packages into one command line everything that you need to compile contracts. So I'll show you now how to actually build a smart contract. So when you have a contract that has been coded by you or someone else, then you can compile it by just issuing this one command line. Cargo Partisia contract build / release. And what this will do is take the Rust program that is the contract, and then it will compile that to WebAssembly, and it will also compile a binary API file that describes the interface of the contract. And you will have those two files after running the compiler, unless of course there's some sort of compile error that you'll have to fix, then you'll see that on the screen. And those two files are all you need to actually put the contract on the blockchain. So the Partisia contract tool kind of packages everything you need into one neat package that makes it easy for you to compile contracts using a single command. One of the things that we are supplying is also a bunch of example contracts that you can start from. So if you go to the link shown on the screen here, and it will also be clickable in the presentation that we will be sharing afterwards, then you'll find the ability to download the example contract package, and that will contain what is on the left here, a bunch of example contracts that kind of show you how to create different components that can actually be used by you to then make the innovative combinations that actually create the next Web 3.0 application. So we are offering example contracts that show you how to make your own tokens, how to execute voting in public, how to run an auction and things like that. But we're also offering example contracts for doing zero knowledge computation, like running a zero knowledge vote where the votes are actually secret, but the result, of course, is public. So you'll be able to download the components, and that will actually help you a lot in creating your own contracts, because we've packaged a lot of best practices into these component or example contracts, and therefore you can find examples of how to do a lot of things, also more advanced things that I'm not going to have the time to touch on today. Finally, the toolbox also has some moving parts that you can actually use to test out your contract or the example contracts. First of all, we have a testnet that is running of the Partisia blockchain. The only difference between the mainnet and the testnet is that the testnet is cost-free, meaning that the gas that is used on the testnet can be obtained without using any real money to buy it. So other than that, the testnet is a complete copy of the code running on the mainnet. So the testnet is a really great tool for testing out contracts before deploying them on the mainnet. There are two front ends available at the moment. There is an MPC Explorer, which is one front end that is a block explorer that helps you see all the blocks and transactions that are executed on the blockchain. The MPC Explorer exists both for the mainnet but also for the testnet. So when you're testing your own contract, you can use the MPC Explorer to see the transactions that are being executed towards your contract. We also have the so-called dashboard. And the dashboard is another front end that is more geared toward developers. It's a little more rough around the edges, but it has some pretty nice features in actually displaying the state of contracts and allowing you to do interactions, sending transactions to the contracts you've coded yourself. We also have the wallet. The wallet is a tool that actually helps you keep track of your accounts and the private keys, and lets you authenticate yourself toward the blockchain. The wallet is usable both for the MPC Explorer and the dashboard. And finally, we offer a faucet. We actually offer two ways of getting gas onto the testnet. There is one way where you actually use the bridge to bring your own coin onto the testnet, but here you can use a free variant of Ethereum called Gurley. But we also offer a faucet that can be used to actually mint more gas for yourself as soon as you have a little bit of gas. So the images you're seeing on the right here is actually an image of the MPC Explorer showing a bunch of blocks, and below you can see maybe you can even see my mouse. I think you can. Below that you can see the dashboard, where you can see we're on a page where we can deploy a contract, and finally we have an image of the wallet. So these tools will help you immensely in actually testing out your contract and seeing how it works. And the advantage of using the testnet and these front ends is that this is exactly the same as the mainnet. So if it works here, you can be sure that it also works when it hits mainnet. And on top of these tools, we offer quite a lot of documentation. There is the developer documentation, which will give you all the information you need to develop your own smart contracts. It will both go through the basics, but also offer deep dives into the exact API and the exact calls that you can make in the different parts of creating a contract. So there's a lot of information to be gained from the documentation. We have a community on Discord, there where you can ask questions and get help, not only from us, but also from other developers who are making smart contracts. So the community is a great way to get help with anything you're stuck with. And then there is a bunch of ways to get more background information, for instance, about how does the MPC work? What is zero knowledge computation? How does Shamir's secret sharing work? Why is blockchain and MPC a really good combination, and so on. And there's both some videos on our YouTube channel, but also this Medium, where there's a bunch of articles posted with background information. So there's a lot of documentation and help available for you to dive into when you want to understand things in depth. That was it for the toolbox. I don't know if there's any questions related to the toolbox yet, Elad.
No.
Great. Then I'll try to dive
Someone
into.
has asked if you can share the Medium link. And you can do that
Yes.
later.
Yeah. I will share the presentation, and the link will. We can probably share the link as well. I don't know if you have the presentation. Otherwise, it can be pasted in the chat. I know Julia is sitting in the presentation, so maybe she can copy it to the chat. Great. I'll move on to how do you actually code a smart contract now. So I'll start by showing how a simple smart contract actually works. And while showing that, I'll also show a little bit about what it looks like when you actually use the dashboard to interact with the smart contract. So for the first part of this, we'll be using an example where we want to execute some sort of voting among a bunch of eligible voters. You can think of a board of a company, a board of an organization wanting to choose whether to take some action or not. So what we're looking at here is a simple majority open ballot vote, meaning that, well, if you have more than 50% of the votes, then the proposal will be accepted and it will be executed. If you have less, then it's rejected. And it's an open ballot, meaning that everyone can see what everyone voted. So what we choose to do is use a smart contract. And the smart contract works like this. The owner of the proposal deploys it on the blockchain and initializes it, for instance, telling who are the eligible voters. The people who are eligible to vote can then cast their vote, and they can do that all the way until the deadline. And they can actually change their mind and change the vote until the deadline has passed. When the deadline passes, anyone can initiate the counting of the votes, and the counting of the votes counts how many for and how many against, and then publishes a result. That's the smart contract that we're going to look at here. So first up, when you want to put the contract on the blockchain, what you actually do is that you create a transaction that holds the contract code, and you then send the code to the blockchain. And if that transaction is valid and you have enough gas to cover it, the contract will actually appear on the blockchain under a new address. So what you see here is actually a transaction being built for the voting contract. You can see we've kind of taken the WebAssembly and the API file that we compiled. We give it a bunch of gas, and then we give the proposal an ID. We say this is proposal number 42. We enter some eligible voters, and we enter a deadline. And then we submit it, and a little while later, the blockchain now has a new smart contract that we can interact with. This smart contract is given an address. You can see the address here in the corner. And under this address, you can now send new transactions that actually change the smart contract. The initial state of the smart contract looks like this. So it knows it's proposal 42. It knows these are the voters that are allowed to vote. This is the deadline. And then it has some empty sections here saying, well, here I'm going to put all the votes as they appear. And this is the result when it is ready. It will be published here. When someone wants to vote on the smart contract, they also do this by sending a transaction. This time they sent the transaction to the voting contract itself. So this is the contract before someone voted. Now one of the eligible voters decide that they would like to vote yes to the proposal. So they send a transaction to the contract saying, I want to vote. My vote is a yes. And then after the transaction has run, the smart contract is updated on the blockchain. And now, as you can see here, a vote has appeared. this user has now voted yes, and it is registered in the list of votes. And just to finish up the example here, then when the deadline has passed, I've kind of jumped forward a little bit. 3 people have now voted, so we have a yes, and a no vote. Anyone can start the counting. This is done by sending a start the count transaction to the blockchain. This hits the blockchain, enters the smart contract. The smart contract does the counting, decides that yes, 2 is more than 50%. So now we update the result, and the result is a true, meaning yes, the vote has passed. So this is kind of what it looks like when the contract runs. And as you kind of saw, that there's 2 important components here. One is the state of the contract. That is the information that is stored on the blockchain, and another is the idea of a transaction, which is kind of sending a message to the contract saying, I want to change something, here's some input, and then the state is updated. And this is what we'll actually learn how to do in the next part, where I talk about how can you code your own smart contract. And the basic programming model is based on, well, the state of the contract and the actions that can then change the state of the contract. So what we want to do when we code a smart contract is that we want to start by specifying what is the state of the contract. And the state is all the stuff that is stored on the blockchain and is publicly visible to anyone. So the way that you actually do it inside the code is that, well, we put this hashtag state in the ROS code, and then we create a struct. And this struct then holds the different parts of the state that is needed for the smart contract to work its magic. So for the vote contract, I've coded these parts of the state. The first is the ID of the proposal that we're voting on. The second is a list of the eligible voters. The third is the deadline for when the vote ends. This is represented in UTC millis, but in effect, it is just a date and a time saying this is the last moment where you can actually vote. The next 2 parts is the actual votes being cast. So this B-tree map is kind of a map from the address of someone to what they voted. And finally, it's the result of the vote that will only be published when the vote is completely done and the votes are counted. So as you can see, the state holds both information about the process that has to happen, but also about the status of things that is ongoing. So the different parts of the state are needed during different parts of the life cycle of the contract. Then what we want to do is say, when you create a contract, what information do you need to put in to actually initialize it when you put it on the blockchain? Because the code for the voting contract can be used multiple times for different votes. But for each vote, we need to kind of put in some different information. And this is the initialization of the smart contract. And what we are doing here is kind of saying, the initialization is, we're telling, we're kind of programming in what information do you need to pass when you put the contract on the blockchain. And for our contract here, what we want to pass is the ID of the proposal we're voting on, the list of the voters that can vote, and the deadline for when the vote ends. So this was the information that was actually put in when we deployed the contract. And inside the code, we are kind of marking the initialization with this hashtag init. And then you're programming a function. And the responsibility of that function is to return a new state. So it kind of creates the first state that goes on the blockchain. And what we're doing here is that this code actually kind of checks a few things. First, it checks that there is more than 0 voters. And secondly, it checks that all the eligible voters are actually unique, because you don't want one person to be able to vote more than once. And with that information, it creates a new state containing the ID of the proposal, the eligible voters, the deadline, and just empty stuff for the rest. And this was everything that was needed to actually be able to deploy contracts and initialize them. Finally,
When submitting the votes, do we have to pay also the gas fee?
For actually doing the voting, no, for each transaction that is sent to a contract, the guy who sends the transaction has to pay the gas fee. So when you deploy the contract, you pay the gas for deploying the contract. When people vote, they pay the gas for voting. If you want more a different gas behavior, there's actually a few ways for you to get around this, but we'll get a little bit more back to that when I talk about contracts, talking to other contracts. But we're starting from a point where when you send a transaction, you have to pay the gas yourself. But what happens to the gas on the blockchain can be controlled to a certain degree by the contract program. The next part you have to code is actually which actions will be available, meaning which types of transactions can I send to the smart contract. And the way you do that is that you program a function in your Rust contract for each of the actions that the smart contract should offer. And what an action does is that it is some type of transaction that someone can send to the blockchain, to the smart contract, and then the action holds the code that actually performs some sort of change of the state. So the way an action works is that, well, you give it a name. This one is called vote. Then you tell the code that it's an action by using this hashtag action. And every time you have a function with the name and the hashtag action, that is turned into an action in the WebAssembly, which will be available for people to call on your smart contract. And what the code has to do is, well, it gets the current state, it gets some parameters. In this case, it is the actual vote that is being delivered by the sender. And then it contains the code that is necessary to update the state. And almost every action always has this kind of pattern where it starts by checking, is this actually a legal or permitted request? Is the sender someone who's allowed to do this? Are we within the deadline, for instance? And so we're kind of checking, is this a request we want to accept? And if it is a request we want to accept, then it changes, then it updates the state and returns an updated state. For the vote here, you can see that we're checking whether the deadline has passed or not. If the deadline has passed, we are not going to accept the vote. And the second thing it does is that it checks that the voter is actually eligible. And if the voter is not eligible, then we're just going to throw away the vote. And finally, if those two things are fulfilled, then it inserts the vote into the list of all the votes that has been cast. And a side effect is that you can actually update your vote, because the insert operation incidentally works in the way that if you do it twice, then you just update. And the second action down here does the counting. So it kind of checks, well, we already counted? Is the deadline passed? And then if those two are true, if we're past the deadline, we haven't already cast it, then it does the counting, checks if more than half voted yes, and publishes the result. So those are the two actions in our voting contract. And with the code that you've seen here, this is actually the entire voting contract. So with that code in the smart contract and the testnet, you will actually be able to create a simple contract that talks to us, that only works in isolation. And this contract is interesting already because it has all of the positive properties of putting a contract on the blockchain, meaning that the contract is not just running on some server somewhere, but running on the entire blockchain running through the consensus, being validated by all of the nodes. So you already get the advantages of the decentralized database here. But to make smart contracts more interesting and more powerful, there's also the ability to create smart contracts that actually communicate with other smart contracts. And this kind of allows you to use a Lego approach to creating systems where you can use a bunch of smart contracts that communicate with each other to make much more interesting and advanced systems. So I'll share a little bit with you about how can you create a smart contract that actually communicates with other smart contracts. And to do this, I've also conjured up an example here. So the example for this is an auction. So what we want to sell something, and we want to sell it to the highest bidder. So we have what's called a simple English auction with open ascending bids, meaning that the bids, the highest bidder wins. Everyone can see what everyone else has bid. So a public smart contract is a perfect place for this. We want to make a smart contract that is the auction contract. It keeps track of all the bids coming in from the bidders. At the end, we will choose the highest bidder, and that person will be allowed to win the auction. Since we are on the blockchain, we might as well make this better than ordinary auctions. And one way of doing that is to actually not only do the bidding in the contract, but actually make sure that the bidder is able to pay if they end up being the highest bidder. And the way to do that is to put the amount that is actually being bid into escrow. So the way we want it to work is that when you deliver a bid, you actually automatically transfer a bunch of tokens from the bidder to the auction contract. And the auction contract then holds on to these tokens in case the bidder ends up being the highest bidder. If the bidder wins, then we can transfer those tokens to the seller. If the bidder does not end up winning, then we can transfer them back to the bidder. And the big advantage of this is that, well, by holding them in escrow, we are 100% certain that the buy can actually go through at the end, because the tokens are being held in escrow on the auction. So to implement this, we kind of need a way for the auction contract to talk to the token contract. And this is what I'll try to show in the example here. And the code you see here is a little bit of the auction contract. It's the code that actually handles the bidding. And the whole of the body of the code is actually about talking to the token contract. So the way that we allow on the Partisia blockchain contracts to communicate with each other is by allowing a contract in the code to actually create a transaction that is then forwarded to another contract. So not only users can send transactions to contracts, contracts can also create transactions that are then sent to other contracts. So what we're doing in our example here is that we are creating a transaction that goes to the token contract. That is the token contract that is used for bidding. And it wants to call the transfer function, or the transfer from function. And we want to transfer money from the sender, that is the guy who's called the bid, to the contract address, that is myself, the auction contract, of the amount that is being bid. And you can see here the bid contains the amount. And then we kind of say done, and we put it in here in the return value. And by returning this value, it actually tells the blockchain, I have a transaction here, I want to forward it to another contract. So this allows the auction contract to automatically, when a bid is received, send a transfer to the token contract that is used for bidding. This is not completely enough for what we want. because what we actually want is that we only really want to count the bit if the transfer succeeds. So what we really want to do is when someone bids, we tell the token contract to transfer the amount of tokens into escrow, and then we kind of wait and see if this transfer was successful. And if the transfer was successful, then we want to update who is the highest bidder. Because if the bidder, for instance, does not have enough tokens, then of course we will not consider that bid. And fortunately, we have a solution for that as well. And that solution is called callbacks. And the callback is kind of like when you send a transaction or several transactions out onto the blockchain, then you can also say, well, when these are complete, would you please call me back? So in the code, you can add a callback. You can see this code at the top is the same as before. We're receiving a bid, and when we receive the bid, we send a transaction to the token contract. It tells the token contract we want to transfer the amount that has been bid from the bidder to the auction contract, so it can hold in escrow. But what we're also doing here is that we are saying, when this transaction completes, please call me back. And when you call me back, please give me a little bit of information as well. I want to know who the bidder was. I want to know the amount they bid. And then I want to know whether this transfer was successful or not. And that is done, that is done by this with callback. And then the blockchain sends off the transaction executed on the token contract. This happens, the blockchain automatically, for instance, handles the fact that they may live on different shards, and that means the transaction has to travel to another shard for the transaction to actually be executed on the token contracts. But when the execution is complete, then the blockchain will make sure to call the callback for you automatically. And it will always be executed if the transaction was executed, no matter if the transaction succeeded or failed. So in your own code, you can create a callback. That is the function that is called when the transaction has completed. And this is the function where you get information about whether this transaction succeeded or whether it failed. So now we're actually ready to create our logic. So what we're doing in our example here is that we are registering the callback, saying I want to call the bit callback function. Then I've created this callback function called bit callback. It receives the state of the auction. It also receives these two informations about who's the bidder and the amount, because we kind of sent them here. And then it receives the callback context. And this callback context can be used to see whether the transaction succeeded or not. So what we do down here is that we simply check, did the transaction succeed? That is the transfer. If it did succeed, then we check whether the bidder is the highest bidder. If he was the highest bidder, then we update the state and say, now we have a highest bidder. So this is the code you will need to call all the contracts and to get the callbacks when a transaction has been completed in another contract. And this is one of the places where the Partisia blockchains works in a different way than the EVM blockchains. So this is one of the places where there will be a slight difference in how you have to do your coding style. Yeah. Finally, I'll try to show how can you actually make zero-knowledge smart contracts. How can you code? How can you program stuff that is executed in MPC? I think this is probably the big thing that we in Partisia are adding to the blockchain space. So hang on for this. Yeah. First up, let me talk a little bit about what is a CK smart contract. Well, a zero-knowledge contract is a contract that does some part of its computation on data that is effectively encrypted or secret. And the way that this actually happens is that you deploy the zero knowledge contract to the blockchain, and at the same, when you do the deployment, not only is the contract deployed, but actually a number of CK nodes is allocated to actually perform the zero knowledge computation. These CK nodes are allocated among the nodes that are running the blockchain who have registered as CK nodes. So they have to put in extra staking to actually become CK nodes, and they have to run some extra software for that as well. The zero knowledge nodes must then stake some of their tokens as collateral to participate in the specific contract that you are deploying. So that means that when you put a zero knowledge contract on the blockchain, you can actually specify how many tokens must they put up as collateral. The collateral is there to make sure that if they, for some reason, do not behave well during that computation, then they can actually be punished. So they're putting money on the table to actually participate in your computation. The way it works is that a public smart contract, just the same type of smart contract as we just saw, orchestrates all the inputs, all the computations. Users of the blockchain can deliver secret shared input to the allocated nodes. So when the contract has been deployed, it is there running on the blockchain. You can use the contract with public inputs as normal, but you can also deliver secret inputs, and they are delivered to these allocated CK nodes. The CK nodes can then perform arbitrary computations on the secret shared data. And the way this is actually orchestrated, they can perform those computations without gaining any knowledge themselves about the inputs or about the results of the computations. At any point during this, after the computation is done, then the contract can actually choose to reveal some of the results of the computation, but that is up to the contract whether the results should be revealed or not. So just a callback to how CK nodes work on the blockchain. Well, a CK node is a special type of node operator that has actually put in extra MPC nodes as staking. Their job is to run these privacy-preserving computations. It is to stake collateral towards the computations they're executing. They also help in producing pre-processed material, which is used by the CK computation, and then they run the computation itself. So the Partisia blockchain is a super nice way of actually gaining access to an MPC network that is willing to put up stake and run your computations for you. So this is a little bit about what a CK smart contract, how it works, what it actually does. And in a zero knowledge smart contract, we have two pieces of code. You have the public smart contract, which handles all the public state, the public actions, and orchestrates the CK inputs, the computations, and the outputs of the zero knowledge layer. And then you have the zero knowledge computation, which is actually the computation that happens on the secret shared data and produces secret shared results. The zero knowledge computation is run by these allocated zero knowledge nodes, and it happens on secret shared data. When a zero knowledge contract has been deployed on the blockchain, then the users can interact with this contract in three ways. Where with a normal public contract, you can only send transactions, and those transactions trigger a public action. But for a CK contract, you can actually interact with the contract in three ways. You can execute a public action just like you can on a normal smart contract. You can deliver a secret input that's going to be part of the computation, and that input will then be, you will be splitting it up into secrets and delivering it to the node running the computation. And finally, you can actually fetch a secret output, because one of the features that zero knowledge smart contracts has is that each secret piece of data is owned by someone. And if you own a secret piece of data, you are allowed to fetch it also from the zero knowledge nodes. The public smart contract has a bunch of things at its disposal as well. That is not in the normal smart contracts. So it can perform public computation like in the normal smart contract, but it can also, whenever user tries to deliver some input, it can accept or reject the inputs. So it can actually do the validation, not on the values because they're secret, but on whether the user is allowed to deliver the inputs. The smart contract, the public part of the smart contract, is the one responsible for saying when the CK computation starts. And it is responsible for choosing whether to reveal the output of the computation or whether to keep it a secret. Before I show you how we code a smart contract, let me show you how to compile it. Because
maybe it's time to actually ask a question that is waiting for you for a long time. Given the ZK computation is a new concept for most devs, is it possible to build a standard smart contract, dApp, and then add ZK computational techniques after, or is it better to build ZK computation into the smart contracts from the ground up? If it can be built in after, is it trivial task?
Yes, that's a good question actually. We have constructed. The reason that we have made CK smart contract the way we have is actually to help do exactly that. So if you start by making the public smart contract, then you can add the CK computation afterwards. So you can create the ordinary smart contract code first that works with the public state and that offers the public the normal actions. And then on top of, then you can change it to be a CK contract afterwards. And all of your public code will still work. So I actually think that is a good approach to start by coding the public parts of the smart contract, making sure they work, and then add the CK stuff afterwards. That would be a good approach. And creating CK is it is a bit daunting. The code is a bit more complex, but I think we have some good examples that will help you. Very often the zero knowledge computation that is needed to do pretty cool things is actually very limited. So you don't necessarily need to do very complex zero knowledge computations to get some very impressive results, because often much of the stuff that happens in a CK contract actually happens in the public part, and you only need to sprinkle a little bit of zero knowledge computation on top to actually make it much cooler than a purely public contract, because it's only the stuff that you need to keep secret or private that has to be in CK. But more on that later. Were there any more questions that we want now, or should I move on?
And we can move on.
Yeah, I'll move on.
Thanks.
To compile a CK contract, the gist of it is that you do exactly the same as to compile a normal contract. So even though a CK contract is more complicated because there's two pieces of code and it has all of this extra functionality, the compile method is the exact same. You do the same command line, and our compiler tool will then under the hood do what is needed to actually compile those two pieces of code. The result of the compilation is now not only a WebAssembly file, but this CKWA file. And this file contains two things. It has the CK bytecode, that is the bytecode of the zero knowledge program that you have coded, the zero knowledge computation. And then it has the WebAssembly code for the public contract. And beside that, it has this API file which describes the interface. And when you kind of have two contract Rust files, one with the public contract, one with zero knowledge computation, you run the compiler and it will produce these two files for you. And then it's ready to be uploaded to the blockchain. Of course, you may get some compiler errors as well, but when you fix those, then you have the stuff you need to deploy to the blockchain. The example I want to show here is calculating the average salary for a group of people while keeping each individual salary secret. So what we want is to deploy a contract to the blockchain that is used for calculating this average salary. Maybe you're someone who's responsible for generating a statistic of salaries among some group of people. You deploy it to the blockchain. After you've deployed it, well, then the blockchain will allocate some CK nodes for you, and they are now ready to handle this zero-knowledge computation for you. All of the respondents that participate in your data collection of salaries can then deliver secret input to this smart contract. And what they do when they deliver the secret input is that they take their salary, they split it into secrets, and then they send these secrets to each of the CK nodes. And they also deliver a transaction to the blockchain saying, I've delivered some input. And finally, when some time have gone by and some people have entered salaries, then the owner can say, now I want to compute the average salary. And this computation is done in zero knowledge. And only the result is published. No individual salary is ever available to anyone, not anyone looking at the blockchain, but also not any of the nodes running the computation. So in our example, it works exactly, again, the same as a normal smart contract. You do a deployment transaction where you upload these files, you add some gas, and then you add a small extra parameter saying this is the amount of stake I want to put on I want the nodes to put up for actually running the computation. The contract appears on the blockchain. It has some public state, but now it also has some CK state, that is information about who's running the computation and how the computation is actually going. And after that, people can deliver their salaries. And delivering the salary, well, we've actually coded the dashboard so that you can actually do the secret sharing directly in the dashboard. So the number I'm entering here, and when I press the submit button, it will automatically be split into secrets and sent to these CK nodes together with the needed transaction. So you can kind of use it the same way you do a normal contract. But of course, if you want to code your own client, then you'll have to use it in a more advanced way where you do the secret sharing yourself. A little bit about how you code these. First, on the CK computations. Well, first up, the CK computations are also written in Rust, even though under the hood, MPC is going on with a lot of complex mathematics and cryptographics. Then what we've done is actually create a Rust compiler that can compile ordinary Rust code, or at least from a subset of Rust, down to this the operations that is necessary to run a CK computation. So the way that you code it is that you code a function that works with special types, and these special types, SDI32, for instance, is a secret shared binary integer that this one is 32 bits long. And what this computation does is that it takes all of the variables and well, it runs over all of the variables that has been inputted, that is all of the salaries, and then it adds them up with the plus operator, and then it returns the result. And here it looks super simple. You just iterate over all of them and return them. But what actually happens under the hood is, as I said, that the secrets are being added up in a way that the nodes don't even know what the numbers they're creating are. They don't know the inputs, they don't know the outputs. And then in the public part of the contract, you can actually then create the code that orchestrates getting the inputs and starting the computation. And what you see here is the code for getting the secret input from one person delivering their salary. So the top part of the code here is the code that kind of verifies whether this input is valid, whether the person delivering it is allowed to deliver it. And the bottom part is something that's called when the input has been completed and all of these CK nodes have actually received input from a person. So we now have this CK on secret input as a new special way of saying, I'm now coding something that handles secret input. And you get some extra, you have some extra data available here, the CK state and the CK, and you can return this CK input definition, which is kind of a definition saying this is the type of input that is being delivered by this person. So what we do here is that we check that every person who's delivering a salary can only deliver a single salary into the computation. And when the input has been completed, we do nothing in this contract. So now we have the code needed to receive salaries from people. And finally, here's the code that is needed to actually run the computation. So this is a normal open public action, but that action actually starts the computation. And the way it does that is by returning this special CK state change start computation at the bottom. So by returning this special value, you signal to the nodes, now you should start doing the computation. So the way the code works here is that the owner calls this. The code then kind of checks, is it the owner? Because if it's not, then they're not allowed to start the computation. Are we already computing? Because if we are, then we won't start a new one. Has at least 3 people submitted secret inputs? Because if less than 3 has submitted, then we don't want to start the computation. And if all of these criteria are fulfilled, then we register how many respondents do we have right now, because we are allowed to count them. This is public information. And then we start the computation, and the CK nodes will go and do their work. Shortly after this, we will be alerted that the computation has completed. So the nodes are doing their thing, doing the computation. At some point, they have a result available, and they will inform the blockchain by actually calling a special action on the contract, CK on compute complete. When that is called, you will get the information about these were the outputs of the computation. So you'll receive the list of outputs, and then the contract can choose to do whatever it wants. In this case, what we're doing is choosing to reveal the value of the output. That is, the output here will be a sum. So what we're choosing to do is to actually reveal the secret. For now, the sum of the salaries is also secret, but we then choose to reveal it. When we signal that we want to reveal it, all of the nodes take their part of the secret and make it public. And by combining all those parts, then we can actually find then we can reveal the underlying actual value. This is also done by the contract by using this CK on variables open function that then gets a list of variables that have been opened, that is revealed by the nodes. And what we do here is that we read out the sum from the revealed shares. We get the number of employees that we recorded a short while ago, and then we calculate the average salary and put it into the public state, and then we signal that we're done with the computation. And now the CK nodes can be deallocated, and we have completed computation of the average salary without revealing any salaries of any of the involved people. That was all I prepared. Now you should be able to, at least with the help of these slides, get the tools you need, code your own smart contract that has interesting actions, make contracts communicate with other contracts to make innovative combinations, and to create zero-knowledge computations when you need them.
Thank you, Jesper. We have a question regarding will there be a hands-on follow along coding workshops as well?
Well, that's the at the very latest, there's the chance to do that when in Paris. But I think if people are interested in doing code along, then I'm sure we can set something up. And remember that we have the AMAs, and every Friday, as far as I remember, it's from now until the 4th of December. There's an AMA where you can ask anything. There is the Discord where you can also ask every problem you have, and other coders will help you, but we are also monitoring everything that is put in there and making sure that you get proper answers.
Awesome, thank you. And that's conclude our time for today. Thank you very much, Jesper. We will also be here tomorrow for front end and back end, same time, and on Wednesday for full stack build, and we will have a weekly AMA on Thursday. Thank you very much, everyone, and have a wonderful morning, day, evening, wherever you are. Ciao.